Most people meet the periodic table as a classroom poster full of tiny boxes, but its real purpose is far bigger than memorization. It is a compressed model of how matter behaves. Each box is an element, but each position is also a prediction. Where an element sits tells you how it is likely to react, what kinds of compounds it tends to form, and whether it behaves more like a metal or a non-metal. That predictive power is why the periodic table appears in chemistry, physics, materials science, engineering, and even parts of biology. It takes overwhelming complexity and turns it into a readable structure. Instead of learning every element as an isolated fact, you learn the logic that connects them. Once you read that logic, unfamiliar elements become less mysterious, because their neighbors and location give clues. So the periodic table is not just an inventory of known substances. It is a framework for turning atomic data into chemical insight. The modern table is organized by atomic number, meaning the number of protons in an atom's nucleus. Hydrogen has 1 proton, helium has 2, lithium 3, and the sequence continues upward. This ordering matters because proton count defines the element's identity. If you change proton number, you do not get a variant of the same element. You get a different element entirely. When scientists arranged elements in proton order, they saw something remarkable. Properties changed in patterns that repeated approximately at regular intervals. That repeating behavior is the periodic law. The word periodic does not mean every property repeats perfectly like a machine cycle. It means recognizable chemical similarities reappear often enough to create structure. The table is a visual expression of that recurrence. It is built so increasing atomic number runs through the chart while recurring behavior aligns into columns. That is why position is so informative. The periodic table captures both progression and repetition at once. To read the table clearly, focus on 3 structural ideas: periods, groups, and blocks. Periods are horizontal rows. Moving left to right across a period increases atomic number step by step, and properties gradually shift as electron arrangements change. Groups are vertical columns. Elements in the same group often show related chemistry because they share similar outer electron patterns, and outer electrons drive most bonding and reactivity. Then there are blocks, the broad regions called S, P, D, and F, which correspond to how electrons fill quantum states. These blocks explain why different sections of the table have distinct personalities, like the transition metals in the D block or the lanthanides and actinides in the F block. So the table's shape is not decorative. It encodes how atomic structure generates chemical behavior. Once you see periods as progression, groups as family resemblance, and blocks as electron architecture, the chart stops feeling arbitrary and starts reading like a map. One reason the periodic table is so useful is that it reveals trends you can follow directionally. Metallic character generally increases as you move down a group and from right to left across a period. Non-metallic character generally increases toward the upper right. These are not random classroom arrows. They reflect how strongly atoms hold electrons and how they tend to interact. Metals usually lose electrons more easily, forming positive ions and often conducting heat and electricity well. Non-metals more often gain or share electrons and frequently form directional covalent bonds in molecules. Because these tendencies cluster by region, a quick glance at an element's location gives a first prediction about its chemical style. That does not replace experiment, but it gives a strong starting model. The table therefore functions like a decision aid. Before running complex measurements, scientists can generate plausible expectations using periodic position and known nearby behavior. Historically, the breakthrough came in 1869 with Dmitry Mendeleev's table, the first version to gain broad acceptance. At that time, many elements were already known, but chemistry lacked a unifying structure that made predictive sense. Mendeleev arranged elements by then available mass relationships and recurring chemical behavior, but his most powerful decision was to leave gaps where the pattern demanded missing elements. He treated those gaps as evidence, not failure. Then he predicted properties of undiscovered elements that should eventually fill those spaces. When later discoveries matched key predictions, confidence in periodic law grew dramatically. This was a major shift in scientific maturity. A list can describe the present. A law can forecast the unknown. Mendeleev moved chemistry from cataloging toward prediction. Even though his original ordering variable was not yet the modern atomic number, his pattern recognition captured a real structural truth about elements and opened the path to the table we use today. The deeper explanation arrived in the early 20th century through atomic number and quantum mechanics. Scientists established that proton count, not atomic mass, is the fundamental identifier of an element. That corrected ordering ambiguities and stabilized the table's backbone. Quantum mechanics then explained why periodicity exists at all. Electrons occupy quantized energy states, and the pattern of outer electrons controls most chemical behavior. As proton number increases, electron configurations evolve in structured ways. When outer electron patterns recur, similar chemistry recurs, and those recurrences appear as group similarities in the table. This connection transformed the periodic table from an empirical pattern into a theory-grounded framework. It was no longer just that the table worked. Scientists could explain why it worked. That integration of observed chemistry with atomic theory is one of the major achievements in science, because it links microscopic structure directly to macroscopic behavior in a single coherent model. The modern visual layout was further refined in 1945 by Glenn T. Seaborg's actinide concept. He recognized that the actinides fit more naturally in the F block rather than being forced into the main body as if they behaved like typical D block elements. This mattered because placement is not cosmetic. Placement signals expected electron behavior and chemistry. By relocating the actinides into a dedicated F block row, parallel to the lanthanides, the table became more internally consistent with quantum structure. The familiar detached rows beneath the main grid are a practical layout choice for compactness, but they also reflect this conceptual correction. Seaborg's revision demonstrates that even iconic scientific tools evolve. The table's core principles stayed intact, yet specific representation improved as evidence and theory sharpened. In science, revision is not weakness. It is how models become more accurate and more useful over time. Another key point is that the periodic table includes both naturally occurring and laboratory-made elements. In nature, elements are found up to atomic number 94, while heavier ones beyond that are synthesized artificially. By 2010, scientists had identified the first 118 elements, completing the first 7 periods of the currently recognized table. But naming and placing an element is only part of the story. Full chemical characterization of the heaviest elements remains difficult, because many of these atoms are produced in tiny quantities and can decay very quickly. When lifetimes are short, direct chemical testing becomes technically challenging. Yet confirmation matters, because an element's table position implies expected properties. If measured behavior diverges significantly, scientists must reassess assumptions. So the upper end of the table is not just a race to add boxes. It is a precision project where synthesis, detection, and chemical validation must align before the structure is considered secure. Looking ahead, scientists expect future discoveries to push beyond 7 rows. But no one knows exactly how far the table can extend. As nuclei become larger, stability problems intensify, and producing new elements becomes harder. Theoretical calculations also suggest that unknown ultra-heavy regions may not follow familiar patterns perfectly. At very high atomic numbers, effects tied to strong nuclear charge can alter electron behavior in ways that complicate simple trend extension. This means periodicity remains real but may become less intuitive in extreme regimes. That uncertainty is not a flaw in chemistry. It is a frontier. Each potential new element tests whether current models remain reliable or need refinement. The table, then, is both an achievement and an active experiment. It records what we understand while exposing where understanding becomes difficult. Its future expansion will likely teach us as much about the limits of current theory as about the elements themselves. Even for known elements, there is ongoing discussion about optimal representation. Multiple periodic table forms exist, including long forms, alternative left-step arrangements, and other geometries that highlight different relationships. The common classroom version dominates because it balances readability, tradition, and practical teaching value, not because all alternatives are wrong. Some designs emphasize electron-filling logic more directly. Others prioritize visual group continuity or pedagogical simplicity. There are also occasional debates about exact placement of particular elements where different criteria can compete. These discussions remind us that the periodic law is the fundamental concept, while table format is the interface used to display it. A representation is judged by what it helps people predict and understand. So disagreement about layout is not confusion about chemistry. It is often a productive debate over which visualization best serves a given purpose, audience, or theoretical emphasis. If you step back, the periodic table succeeds on several levels at once. It is a classification system, a predictive engine, and a bridge between chemistry and physics. It organizes known elements, forecasts likely behavior of unfamiliar ones, and reflects deep atomic structure explained by quantum mechanics. It also carries historical depth, from Mendeleev's predictive gaps to modern superheavy element research. Most importantly, it changes how we think. Instead of seeing matter as a giant list of disconnected substances, we see a patterned landscape where structure generates behavior. That shift from memorizing facts to reading relationships is why the periodic table remains central to modern science. It is not static knowledge trapped in a textbook. It is an active framework that keeps guiding discovery. The better you understand its logic, the more clearly you can interpret chemical behavior, evaluate new findings, and appreciate how a simple grid became one of humanity's most powerful scientific maps. If you found this helpful, please like this video and subscribe for more explainers.